to introduce yet another crucial, key, important concept in basic probability, we're going to return once more to the pedestrian crossing problem. This idea of stochastic independence is going to come back for us and make our lives actually significantly easier as a result. And we'll see it again and again and again, maybe not explicitly stated in a lot of situations. Yes, in the first several modules it will be, but as we get on later in the course, it'll be a somewhat implicit and stated assumption about the role that stochastic independence is playing. And in this context, remember that in the pedestrian crossing problem, we had ultimately really two random variables. The time gaps themselves, right, and that was capital T, and it came at us in possible outcomes of 3, 6, 9, 12, and 15 seconds. Right? And then we had the crossing time, let's call that C, and in example intro 2.3 we talked about that being 8, 10, 13, and 16 second possible outcomes. And if we ask the kind of question of, well, what's the chance that we were to reach into the bag and we'd have a gap of 9 seconds and we required a crossing time of 10 seconds, then we're doing what's called a joint kind of question, right? Because two random variables, and that means two simultaneous outcomes, right? And so if it turns out that this probability can be determined by multiplying the marginals, right? The probability that the time gap is 9 times the probability that the crossing time is 10, and that's true that this breaking apart, if this probability here, somehow we know it, and it turns out that it's equal to these product of the product of these marginals, and that is going to be true of the joint for all combinations of the two random variables, then we have stochastic independence. Right? And one way to say that is that knowing something about one random variable tells me nothing probabilistically about the other random variable. And that might actually make sense in the context of how long does it take to get across versus what the traffic gaps are. Right? No functional dependence, or would they? It depends on how we think about that. So let's generalize this first and then come back to this to try to decide whether or not that does make sense, independence for this kind of a situation. Right? So in a more formal kind of way, two events, let's call them A and B, are independent if, right? Independent if under the following conditions here. Probability that A given B, so that's the conditional probability of A conditioned on event B happening, if that is equal to the same as the probability of A alone without any information about B, and probability of B given A is just equal to the marginal of B, right? Then we end up with that when we look at the joint occurrence of A and B, that's going to be the product of those two, right? If these are true, then A and B are stochastically independent. We oftentimes don't say stochastically independent, we just say they're independent. All right, now, one reason this works is, remember, from the total probability approach theorem, we could have written this as probability of A and B, that'd be the probability of A given B times the marginal of probability B. And if it turns out that A given B is equal to probability of A, then bam, we've got this one right here. right? And vice versa, we could say A and B, so probability of B given A, and then times the probability of A, same thing, substituted in. One of the keys here is that just because probability A given B is equal to that does not necessarily mean this one is true as well, right? So let's go back and put this into the context of this and think about it in terms of physical kind of significance, because your typical pedestrian is going to actually look at what they think the time gap is, and they'll adjust how fast they go across depending on what the size of that gap is, right? We actually have lots of data collected that demonstrates this, not only for pedestrians but also for drivers trying to get across an intersection, that the longer they have to wait, they will change what we call the acceptance gap, right? And we're willing to take a shorter gap because we're tired of waiting, right? And so there is from a behavioral standpoint, there is a linkage between the two. And so we might expect in that case that the probability distribution of the crossing time could be conditioned upon what the size of the gap is, right? But the other way around might not be the case, right? The probability of the distribution of the time gap is not necessarily at all dependent upon what the capability of the pedestrian is. Or is it? Actually, it might be in certain situations as well, right? Because there are some states and or municipalities that have laws that say it doesn't matter where in the street a pedestrian crosses, if they step out, you, the driver, must stop, right? You have the responsibility of stopping regardless of whether the pedestrian is doing something legal or not, right? Kind of an interesting situation. And in those cases, you get then a real mixed bag here where A and B, or T and C in this case, would not be independent at all, and we'll have to do something else to come up with this joint distribution. That means our data collection has to be thought through far more carefully. I can't just go out and measure people's capability to cross a specific distance without regard to what the traffic situation is. I have to think about the context, and that makes then data collection, of course, much more complicated to do. And it represents how difficult creating some of these models can be in the big picture. Now, from the standpoint of additional practical application here, stochastic independence, when it does happen, or if we assume that it is the case, makes our life a lot easier, because all of a sudden now this joint or intersection event, you might call it, that becomes then just a simple product of two different marginals, and usually it's a lot easier to come up with these models than it is to do that one. And when we get into doing hypothesis testing and looking at random samples and that sort of thing, and start looking at sampling distributions, which means what's the distribution of the sample mean, sample average, those sorts of things, independence between really the definition of randomly selected samples will have an independence that's assumed there, and that will be critical as we start looking at what the distribution of some of these sampling measures are down the path.